new unit. This one's on electrochemistry. This, I would say, is again kind of a extension of what we've already done on thermochemistry and equilibrium to a certain extent. We're going to see Q again. We're going to see delta G again. So all these concepts are going to be coming back. Few housekeeping things. My plan is to make a short assignment that I'm going to post today, have it due Tuesday, the regular time. And this is going to be an assignment based on what we're going to cover in today's class, which is going to be oxidation numbers and redox reactions. And it's not going to be very long because I didn't give you a whole lot of time because we kind of missed 2 classes already this week, one for the midterm and one for the A-Lab visit. Next week is the week that we have scheduled for the oral tests. Now, I haven't spoken really about that yet, although I think you're familiar with the concept because I believe you have done this already last semester. My plan is to do something kind of similar to what was done last semester. What I'm going to be doing is sometime today, setting an email out where there'll be sign up times, and you can pick a slot and jump in. I think what happened last year, and by last year I mean last semester, is that Dr. Banks gave you some questions in advance, about like 5 minutes in advance. Is that right? I kind of like that idea. I think I might do something similar. So it's not like you're just seeing it for the very first time when we meet, but you'll have a bit of time to look at it and think about it. So I will send an email out today with some parameters around that, along with a notification when the short assignment, mini assignment, we'll call it, goes live. I have not graded the midterms yet. I'd like to have those done before Monday's class, if possible. It depends how bad my life blows up today, but I think I'll have time today to handle those, tackle those. I think that's it. I don't think I'm forgetting anything. And if it comes to me, I'll just send you an email. Great. So we're doing a new unit. It's not Unit 5, it's Unit 13. Whenever we move things around or change the names of things, I never think to change the number on the opening slide for whatever reason. I just never do. But yeah, this is like Unit 13. I guess it's Unit 5 if you started from kinetics as Unit 1 for this semester. So we're 5 in. But we're going to do a bunch of different things here, and we're going to start off talking about redox reactions, what it means to have a redox reaction, what's a reduction, what's an oxidation, and things like that. All right, so electrochemistry really is a branch of chemistry dealing with what we call electron transfer reactions. So the reactions where what's happening is electrons are moving from one compound to another compound. In fact, there's actually a whole field trying to describe how electrons can get from one species to another. And there's different mechanisms and all this sort of thing, which you might get into maybe later on in inorganic chem, but we're not going to get into that now. There's actually a Canadian chemist by the name of Rudolf Marcus who won a Nobel Prize for helping understand how electron transfer reactions happen. Won't talk about Rudolf Marcus, though. We don't need to hear about him. Okay, so really what we're going to be doing is converting what we call chemical energy to what we most commonly refer to as electrical energy. And electrical energy really is just flow of electricity, flow of electrons through some conductive material from a place of high potential towards a place of low potential. And when we do this using a chemical reaction, which is what happens in batteries, this involves transfer of electrons between different chemical species. And when you have one of these electron transfer reactions, you're always going to have a species that will give up electrons, lose the electrons, and something else that has to gain them. And all of the ones we're going to be looking at, the number of electrons are actually constant, right? So you can't, every electron that gets lost by one thing gets gained by another thing. I will say, though, it's actually technically possible for something to lose an electron and for something else to not gain it. There's actually a reaction if you take something like sodium metal and you dissolve it in ammonia. It goes to Na plus Aq plus an electron. I guess it's not really aqueous because it's not in water. It'd be whatever the word of aqueous is when it's in ammonia. But this will dissolve and you have what's called solvated electrons, where you have electrons that are just free. And if you've never seen a solution of electrons, they're blue in color. So you can actually make just free electrons like that. But we're not going to be dealing with examples like this. We're going to be dealing with examples where something else comes along and plucks that electron out and gains it. When something gains an electron, we call that reduction. And when something loses an electron, we call that oxidation. So to make this easier, what we do is we take all of the atoms involved in the reaction and we assign to these oxidation numbers. Okay, or sometimes we call these oxidation states, but I'm going to call them oxidation numbers. So generally speaking, here's a general rule of thumb. When you have a compound and you're assigning oxidation numbers, the more electronegative an atom is, the more likely it is to have a negative oxidation number. And whenever you have something that's electropositive, which would be sort of on this direction on the periodic table, you're more likely to have something that has a positive oxidation number or positive oxidation state. So we have a set of rules, and these rules are, you learn the rules and you apply them. Once you get familiar with these rules, they become pretty straightforward. First rule, and these are rules of priority, meaning if something in rule 1 works against something in rule 4, rule 1 takes precedence. First rule says that the oxidation state of an atom in an element, in a pure elemental neutral state, is 0. Like Cl2, both chlorines are 0. Sodium metal, oxidation number is 0, right? And actually, if you look at this, some of these rules can probably be combined. So the second rule says that if you have a monoatomic ion, single atom, that whatever the charge is going to be its oxidation number. So sodium plus would have an oxidation number of +1, chloride would have -1. So you could kind of combine rules 1 and 2 and just say whatever the charge is, that's the oxidation number, because these are all neutral. The third one is an important rule. The sum of all the oxidation numbers or states in all atoms in a molecule will always add up to 0 if the molecule is neutral, or if it's not neutral, if it's got a charge, it'll add up to whatever the charge is. So in the case of water, for example, we would say that whatever the oxidation numbers are for hydrogen and oxygen, they have to add together to make 0. For something like hydroxide, they would have to add together to make something that's -1. In compounds, metals will have positive oxidation states, generally speaking. Group 1 metals, which is the alkali metals, first column in the periodic table, all are always +1, unless they're in rule 1, which means they're an element, in which case they're 0. Whenever they're in a compound, they're always +1. Group 2 metals, which are the alkaline earth metals, beryllium, magnesium, calcium, strontium, those all will have oxidation states of +2, always. A couple of rules here that kind of pen in what we're able to apply. Third one says the oxidation state of hydrogen in a compound is +1 or -1, depending on the electronegativity of what it is attached to. So if it's attached to something that's more electronegative than it, then it will have a positive oxidation number. If it's attached to something that's less electronegative, it'll have a negative oxidation number. So maybe an easy rule of thumb to think here is it's +1 when it's attached to a nonmetal, and it's -1 when it's attached to a metal. So if you have something like CH4, we would say the hydrogen here, because it's attached to a nonmetal, it's going to be +1. So that means the carbon here is going to be -4, because We have 4 hydrogens. Each of them are +1 for a total of +4. We know this is a neutral molecule, so the sum of everything has to be 0. So that means the carbon has to be -4. An example where hydrogen would be negative would be something like calcium hydride, where in this case it's bonded to a metal. So we would say the hydrogen is -1 and the calcium is +2. And it's +2 because of rule, I guess, number 2 here, says that group 2 metals are always +2. And these add up to give you the charge, which is an oxidation state of 0.
So is that -1 to -2?
It's -1 per hydrogen. So total of -2 because there's 2 of them. Yeah. For nonmetals, they get a little more complex. Fluorine always has an oxidation state of -1, unless it's atomic, like molecular fluorine, F2. So any molecule, any compound where fluorine is part of it, it's always -1. I think there's probably no known examples where that's not the case. Oxygen is almost always -2. An exception is when it's part of a peroxide, when it has an oxygen-oxygen bond. We'll call this R1 and R2. So when you have this peroxide linkage, like you would have in hydrogen peroxide, then it has an oxidation number of -1. Otherwise, -2. The other group 17 elements, these group 17 is the halogens. This would be like chloride, bromide, iodide, astatine. These are usually -1 unless they're a central atom. Do you know what this periodic table is incomplete, but there's another halogen below the astatine? Is it nionium or I think moscovium is the last one, 118, 117. Fluorovium maybe? Anyway, some weird ones down there. They're usually -1 unless they're a central atom. So in a central atom, if you have something like, ClO4 minus, like in the perchlorate anion, then it's not going to be -1 in that case because it's a central atom. The other group 16 elements often have an oxidation state of -2. The rules are starting to get a little fuzzy at this point. So this means things like sulfur or selenium, they're often -2, but they're also often not -2. So with this set of rules, we can generally come up with an oxidation number for any atom in a molecular species. Because there's a whole bunch that we didn't talk about. We didn't talk about the transition metals. We didn't talk about a lot of other elements. I don't know what that's for. Okay. It's from the projector, not from my screen. It's not showing up here. It's just showing up there. So it's producing it. Oxidation states. Let's do an example where we assign some of these numbers. So the first one is H2SO4. The first rule I would go to here is look at the hydrogens, because the hydrogens were in the precedence order of those rules, the first one we came across. And we said that if it's attached to a nonmetal, generally speaking, hydrogens are +1. Let's go with +1 for the hydrogen. Sulfur, we said, was often -2, but also often not -2. So let's deal with sulfur last. We do have oxygen, and oxygen, we said, is almost always -2. So if you multiply that out, we have +2 for the 2 hydrogens, -8 for the 4 oxygens. And we know that the sum of all these numbers has to equal 0 because that's the charge. So we can work out then that sulfur has got to be +6. Then if you add up all the oxidation numbers, you're neutral. There we go. We got the oxidation numbers for all 3 atoms in H2SO4. Next, we can look at nitrate. Applying these oxidation numbers is actually, it's easier than, let's say, for example, drawing the Lewis structures. But again, it's similar. You're following a kind of a set of rules. Follow the rules, it'll work every time. Oxygen is always -2. There's 3 of them, so we have -6. The sum of all of the oxidation numbers in this molecule have to add up to the charge, which is -1. That means the nitrogen is going to be +5. NaIO3, neutral, sodium iodate. The sodium will always be +1 because it's a group 1 metal. That's rule 4. The oxygen is always -2, and there's 3 of them, so let's say -6 for the total there, +1 for the sodium there because there's just 1 of them. So the iodine here has to be equal to +5. So that all of these added together is 0, which is the charge on the molecule. So usually you can figure out 1 or 2 of the atoms based on the rules, and then you can figure out the one that's not on the list based on the fact that they have to add up to the charge. Last one is FeO, and we know that iron typically comes in 2 flavors. You can have iron 2 or iron 3. But this case, we know that the oxygen is -2. That means the iron has to be +2. So we would say the oxidation number on the iron is +2. And in fact, that tells us that we're dealing with an iron 2 species here. So these oxidation numbers we're assigning for these metals connects back to the, the different oxidation states of these compounds that we talked about right at the very beginning of the year. By we, I mean you, because I wasn't teaching you then. But yeah. Great. So we can assign oxidation numbers now. That's the first step in what we need to do, which is track the electron flow when we're doing one of these redox reactions where the oxidation numbers are changing. And maybe that's another definition I could give about one of these redox reactions. A redox reaction is one in which oxidation numbers or oxidation states of the reacting species will change, either go up or go down. If an oxidation number goes up, then we say that it's losing an electron and therefore it's undergoing oxidation. So an increase in oxidation number is oxidation. And if it gains electrons, its oxidation number goes down. That would be a reduction. You might have heard before the Leo the lion says "gur." You heard that? It's just easy way of remembering which one's oxidation and which one's reduction. You lose electrons, it's oxidation. If something gains electrons, it's undergoing reduction. And I remember we learned this phrase in high school, but it wasn't in chemistry. It was in biology. I forget what we were talking about, whether it was citric acid cycle or something like that. I don't know. Yeah. So here's an example of a redox reaction where we have chlorine gas, Cl2, dissolved. Well, shouldn't say it's a gas. It's dissolved in water. It's aqueous, but it's molecular chlorine. And it's reacting with 2 iodides to make 2Cl- and I2. And so if you track the oxidation states, those are the numbers there in green. Chlorine, Cl2, goes from an oxidation number of 0 to an oxidation number of -1. So if the chlorine has its oxidation number go down, that means it's undergone reduction. For the iodine, depends where you're from, its oxidation number has increased from -1 to 0. That's oxidation. Great. One thing that we often do is we break these redox reactions out into 2 separate reactions that can be added together. And we take the species that have the same atoms and we put them together in one equation. So this equation here we can break up into the oxidation half reaction, which only involves the iodine, as well as the reduction half reaction, which only involves the chlorine. So we could say that the iodine one, you have 2 iodides, and they are going to make I2, plus 2 electrons, which are liberated. So it's losing those 2 electrons. The chlorine reacts with 2 electrons to make 2 chlorides. And you can see if you took those 2 reactions and added them together, canceled the electrons, you would just get your overall reaction that you see up there. So this is an important method because what we're going to be doing next is balancing redox reactions. And balancing redox reactions, I'll say this, on the surface at least, it looks 10 times harder than balancing a normal reaction. But in actuality, it's easier than balancing a normal reaction because there's a procedure you just follow, and the procedure works every time. So the procedure has lots of steps and is generally more work than balancing a reaction. But yeah, you just sort of, once you know the steps and you can follow them, you're kind of done.
Why is it like 2 electrons?
Why is it 2 electrons here? So basically the 2 electrons are being added to either side here because for the half reactions, what you want to do is balance the charge. So over here we have a whole full charge of -2 where the iodide is 0. So we need to have 2 electrons here to have a balance of charge on both sides.
So for half reaction.
Yeah. So half reactions have to be balanced within themselves. And then when you add them together, the sum of the oxidation and reduction, that sum also has to be balanced. And that's the only way you can balance a half reaction, is to have electrons as kind of like a reagent or a product. Cool. Just a little bit, a note here on terminology. We often talk about in chemistry different chemical substances as being oxidizing agents or reducing agents. So an oxidizing agent is something that will oxidize something else. And if it oxidizes something else, it, in the process, becomes reduced. So whatever gets reduced is the oxidizing agent. So it's a little bit kind of a backwards thing. But for example, O2 will oxidize all kinds of things. Like iron, it'll oxidize iron to make rust. So we would say that O2 is an oxidizing agent, but the oxygen itself is getting reduced in the process. Okay, oxygen will typically go from an oxidation number of 0 to an oxidation number of -2. There we go. So we're going to be looking at how to balance these redox reactions. And I already kind of suggested that what we want to do is take the redox reaction, first of all, and split it into half reactions. We are going to be exclusively looking at redox reactions that are taking place in water. That's the most common thing because water is a great medium for redox reactions, because redox reactions necessarily involve ions, or almost always do involve ions. And most solvents are not good at dissolving ions, but water is great. The other thing, as we will see, many redox reactions either produce or consume H+, and water is a fantastic solvent to either supply H+, or accept H+. It's produced by a reaction because it can act as either an acid or a base. So this method that we're going to be using to solve redox reactions is called the half reaction method. There are many different methods that people use. If there's another method, if you've done this before and you have a different method that works for you, please feel free. In my opinion, of the different methods that I have seen, the half reaction method is probably the easiest to apply and works most consistently. But as I say, there's other ways we can do this. And there's a number of steps that we're going to follow. And once we go through the steps, we'll go through a couple of examples. First, I think what we need to do is realize, I said these are done in aqueous solution. Aqueous solutions typically are either acidic or basic. And when I give you one of these questions, I will often say, balance this reaction if it's in acidic solution or if it's in basic solution. If it's an acidic solution, then there's sort of additional H+ around. If it's in basic solution, then there's additional OH-. So step 1 says identify what is being oxidized and reduced and assign all of the oxidation numbers. So if you assign the oxidation numbers, whichever one has its oxidation number go up, it's being oxidized. Whatever is going down is being reduced. Many things will not have their oxidation numbers changed at all. So they're not being oxidized or reduced. Step 2, once you've done that, whatever is being oxidized and whatever is being reduced, split them apart, like we talked about, into those half reactions. So you have your oxidation half reaction, your reduction half reaction. Balance all the elements that are present in there, except for oxygen and hydrogen. Because we're in water, we have a separate step for those elements later on. So next, what we want to do is balance oxygens. And to balance oxygens, we need to add waters, enough waters to one side of each half reaction until you have the same amount of oxygens on both sides. Then what we're going to do is balance the hydrogens by adding H+ to one side or the other, whichever side needs the hydrogens. If you're under acidic conditions, that's all you got to do. Add the hydrogens to one side or the other. If you're in basic conditions, there kind of is an extra step where you start out by adding the H+ to each side. Then what we do is we add hydroxides to both sides to neutralize all of the H+. Wherever they neutralize, they turn into waters. And that's that. Step 4 is we balance the charges now for both half reactions. You want to balance the charge on each side of each half reaction by adding electrons to one side or the other side. Then what we eventually want to do is recombine these half reactions, and that's done by adding them together, but you can only add them together if they have the same number of electrons transferred in each half reaction. So what you might have to do is multiply one or both half reactions by some constant. So you multiply everything through by some factor until you have the same number of electrons on both sides. I remember doing this in like, was it grade 6 or something? We called it like lowest common multiple. Greatest common factor, lowest common multiple. That's like burned into my head. I think this would be a lowest common multiple situation. Then you just add them together, cancel anything that appears on both sides, and you're done. I guess just the last one is check to make sure you did it right. And to check to make sure you did it right, just make sure you have the same charges on both sides, the same number of atoms, and all those sorts of things. So this does seem kind of like onerous. You know, there's kind of a lot of steps here, 3 pages of steps. But once you've done a couple of examples and get the procedure down, I can give you absolutely any example, and you crank it through the system. You apply the steps, you do it. It's not like I could give you a hard example or an easy example. Every example is the same. Okay, so let's look at an example. This is what the question is asking. Write the overall balanced equation when SO2 is converted to SO42-, which is sulfate, and Cr2O7 is converted to Cr3+ ions, and we're under acidic conditions, we are told. So what we need to do is write out the first 2 half reactions, and we're kind of given the 2 half reactions. We have the sulfur half reaction and we have the chromium half reaction. First thing we need to do is determine what the oxidation states are in these examples. Well, we know oxygen is -2. That means for the sulfur, it's got to have an oxidation number of +4. Because there's 2 oxygens times -2 is -4. The whole species is neutral, so the sulfur must be +4. On the other side, we have oxygen is still -2. There's 4 of them for -8. That means the sulfur must be +6. Because the +6 and the -8 have to add up to give you what the charge is, which is -2. So the sulfur is going from +4 to +6, so it's being oxidized. Next, we have the chromium side. We could say that the oxygen here is -2, and since there's 7 of them, that's -14. The Cr2 has to be a total of +12 because the +12 and -14 has to add up to the charge, which is 2-. There's 2 chromiums, so that means each chromium is going to be +6. And then chromium 3+, pretty straightforward, it's just +3. The charge is equal to its oxidation number. So it went from +6 to +3, that's a reduction. Perfect. So step 1, apply all the oxidation numbers to everything so we figure out what's being oxidized and what's being reduced. The next thing we need to do is balance everything except for oxygen and hydrogen. So for the first one, the only thing besides oxygen and hydrogen is sulfur, and it's already balanced 1 and 1, so we don't need to do anything. The second one, we have Cr2O7, 2-, so there's 2 chromiums on the left. On the right, we just have 1. So to balance the chromiums in this step, we just need to put a 2 in front of the Cr3+. So that's step 2 done. Like some of these steps, you run through them really quickly. It's not like a big laborious process every time necessarily. Step 3, what we need to do is balance oxygens by adding waters to one side or the other. So for the first half reaction, you see there's 2 oxygens on the left, 4 oxygens on the right. To balance oxygens, we need 2 waters on the left. So we just add 2 waters to the left side. So now they both have 4 oxygens on both sides. In the next step, we have 7 oxygens on the left. So we need to add 7 waters onto the right. I think we did 2 steps here at once. So we added the oxygens to both sides by adding waters. The next thing we need to do is balance H+, and you balance H+ just by hydrogens by adding H+ to one side or the other. On this side, we have 4, so we add 4H+ to the right to balance hydrogen. On the right here, we have 14 hydrogens on the 7 waters, so we add 14H+ to the left. So at this stage, we have all of the elements, or all the atoms are balanced. What's not balanced are charges. But the oxygens are balanced, the hydrogens are balanced, and all the other atoms are balanced as well. Okay. Step 4 says balance the electric charge using electrons. So what we want to do is add electrons to one side or the other. For the first half reaction, notice that the total charge on the left is neutral, no net charge. But on the right, we have a -2 plus +4. So we have a net charge on the right of +2. So to balance the 2 sides here, we need to add 2 electrons to the right side. The next one down, if you add up all the charges on the left, you get +12, 14 plus, -2. And on the right, you have +6, 2 times 3 plus, which means we need 6 electrons to put on the left-hand side to balance the charge in that half reaction. Great, so now what we want to do is combine these two. We want to add them back together, but you can only add them back together if they have the same number of same number of electrons on both sides. Because we don't want electrons being like a leftover reactant. We want them to cancel when we re-add them. So what we need to do is multiply the first half reaction by 3, triple everything, so that we go from 2 electrons to 6 electrons. And when we do that, we get the following numbers. Next, what we can do is basically just add those 2 things together. And if you do that, the electrons cancel out. But that's not the only thing that cancels out. Look at the waters, right? Or sorry, the H+. We have 14 here, and we have 12 here. So what we can do is cancel out 12 H+ from each side, and that 14 becomes a 2. Be 2 left over on that side. For waters, we have 6 here on the left and 7 here on the right. Why don't we cancel out 6 from both sides and just leave 1 on that side? So I think that's everything that can cancel. Now we can get our total balanced redox reaction by just writing out what remains. 3SO2. I'm just going to simplify and not write in the states of matter. Cr2O7 2-. plus 2H plus 3SO4 2 minus plus 2Cr3 plus 1 water. Is it. So this is the point where we would check to make sure it's balanced. We would say, okay, well, we got 3 sulfurs, we're good. How many oxygens? We have here, I guess that's 6 plus 7 is 13. Here we have 12, 13, and so on. You can go through all the different species, make sure the charges add up, make sure all the elements add up, and you have a balanced reaction. This is good. Our plan worked here. Let's do another one. Okay. MnO4 minus, and here's what I'm going to do. I'm going to give myself a little bit more space to write with. So what exactly do we have there? We had MnO4 minus C2O4. Mn2 plus and CO2, and we are under basic conditions. So what we can do at this point is we can go ahead and assign all of our oxidation numbers, and that will tell us what, I mean, it's pretty obvious what's going to be split into half reactions. We know the manganese is going to go with the manganese and the carbon with the carbon, but all the same, we can say that oxygen is -2. With 4 of them, that makes -8. That means the manganese needs to be +7. Only showing a loading screen. Does anyone else see anything besides a loading screen? Let me unshare and share again. Looks fantastic on this end. Does that work better? Awesome. All right. So the manganese is +7 because +7 -8 is -1, which is the charge. C2O4, I believe that's called oxalate. And if you buy, there's a product you can buy called Barkeeper's Friend, which is like a cleaning product, which is oxalate. That's -2 because oxygen's almost always -2. 4 of them is -8. That means the 2 carbons need to be +6, right? Because they add together to give you the charge, which is -2. And since there's 2 of them, that means each carbon is +3. The manganese is +2. The CO2 is -2, which is -4, so the carbon becomes +4. We can split this into half reactions. We see the manganese goes from 7 to 2, so it's undergoing reduction. So I'm going to use blue. And the other half reaction, and this one is the reduction half reaction. We also have the C2O4 2 minus CO2 half reaction. Okay, so first step is we need to balance all atoms that are not oxygen and hydrogen. And the first one, we just have 1 manganese on each side, so we're good. Second one, we have 2 carbons on the left. We need 2 carbons on the right. So let's use green. We're going to put 2 carbons on the right as well. That much is balanced. Now we want to balance oxygens by adding waters. So in the top one, we have 4 oxygens on the left, 0 on the right. So we need to add 4 waters on the right to balance oxygens. On the bottom, we have 4 oxygens on the left, 2 on the right. Actually, 4 on the right, too. We have 4 on the left and 4 on the right. So we don't need to add any waters to the second one. This one is the oxidation, by the way. Now we balance hydrogens by adding H plus to one side or the other. And we have 4 waters on the right, which is 8 hydrogens. So we need to add 8 H plus, the left side. Down below on the second one, we don't have any hydrogens on either side, so we don't need to add any H pluses. Great. Next, what we want to do is make sure our charge is balanced on both sides, and we balance charges by adding electrons. So in the top example, you can see we have a total of +8 minus 1 is +7. I'm going to make that red. This whole side is +7. And on the right-hand side, this whole side is +2. So what we need to do is add electrons to the left side to balance the right side. And the number we need to add is 5. Okay, that should balance up our charge. Down below, we have 2 minus on the left. So we need to add 2 electrons on the bottom side. Great, so I think we're done. We've balanced all atoms besides oxygen. We've added waters to balance oxygen. We've added H plus to balance H plus, and then we added electrons to balance the charge. And everything is looking good so far to me, I think. So we want to add these together, but we can't add them together if we have, unless we have the same number of electrons on both sides. The top one has 5, bottom one has 2. That's not going to be good enough. So what we need to do is find the lowest common multiple, which is going to be 10. So what we're going to do to the first one is multiply everything through by 2. And we're going to take the second one and multiply everything through by 5. That will leave us with 10 electrons in each. Then they'll be able to cancel. So that becomes 2 MnO4 minus plus 16 H plus 10 electrons. Adrian says, don't we have to add hydroxide to balance out the H plus? And the answer is absolutely yes. I find it easiest to do that as the very last step. You could have done it earlier, but you could also wait to the very end and do it at the very end. You do what you prefer. This becomes times 2, 2 Mn2 plus 8 H2O. Next, we have 5 times, so we have 5 C2O4 2 minus goes to 10 CO2s plus 10 electrons. Now we're ready to add these together. What we can do is cancel the 10 electrons now. That's all the cancels though. So then we're ready to add these two things together. 2 MnO4 minus plus 16 H plus 5 C2O4 2 minus 2 Mn2 plus 8 waters plus 10 CO2. Now this is the point where we have to account for the fact that we're under basic conditions. So Adrian asked in the chat, why didn't we balance the H pluses earlier on with hydroxides? We definitely could have, and it definitely would work. The reason I like to save it until the end is because that makes the process for acid and base identical all the way up until the very last step. It's like the base has one extra step to deal with, but up to that point, acid and base processes are exactly the same. So to account for the fact that we have base, what we need to do is add hydroxides to each side to cancel out the H plus. So there's 16 H plus on the left, so what we need to do is add 16 OH minus, and if we add them to the left, we have to add them to the right as well. Now we know that H plus and OH minus will react with each other to make water. So those go and are replaced with 16 waters. Now we look to see if there's waters we can cancel, and we have 8 on the right, 16 on the left, so we can cancel out those 8 waters and leave 8 behind here. So that's what we need to do, this extra last step, cancel out the H pluses at the very end when we're under basic conditions. Great, let's just rewrite it to make it a little neater looking. 2MnO4 minus plus 5 C2O4 2 minus plus 8 waters goes to 2 Mn2 plus 10 CO2 plus 16 OH minus. Great, I think we're done. You can always check to make sure everything's balanced. -2, -10, +2, 16. Looks good to me. Wonderful. We now know how to balance reactions both in acidic and basic conditions. So I'll have an assignment up sometime today based on oxidation numbers, balancing redox reactions, and we'll move forward from this on Monday. Cool. Any final questions? No, great. Balancing these are actually kind of fun once you like get them. I don't know. Sometimes you get questions that you can just like follow the process. For some reason they're like satisfying somehow.
I like that with like lung division.
Yeah, lung division's like that too. You just go through the steps and you follow them, and when you get it, like it seems daunting at first, and you're trying to keep all the steps straight, but once you got to figure it out, it's like just go through the procedure. Great. I'm gonna turn off our recording, and I think I need to. I don't know if I have